All right, 14.3 is all about local linearity. And when we talk about linearity, don't think about lines. We should be thinking about planes here instead of lines. So local linearity, tangent planes, and then this thing that's called the differential. All right, so what I've started out with here is I set up a spreadsheet where it's evaluating the function f of x, y is equal to x squared plus y squared. And I've just taken some different values of x and some different values of y and set up a table. Right, and here I wanted to increment the x's and y's by the same amount, and I set it up where I've got this increment over here, h is equal to 1 in this case. So that just says, you know, go by ones across here. And then I set it up again where we increment by 0.05. And then we take that a little bit smaller. We go by 0.1 and then 0.01. Right, and what I want you to notice here is we're going to be interested in finding out something about at the point 2,3. Okay, and if you think about starting at this point 2,3 and then traveling to the next point, traveling to this point, right? So we incremented by 1 on the x and we went up by 5. And then we increment by 1 again and we go up by 7. Right, you should recognize that going from 13 to 18 to 25, that's not a linear progression there. Okay, we're stepping up a little bit and then stepping up a lot more. All right, and then going down this way, as we go from 13 to 20, that's a 7-step jump, and then a 9-step jump, and then going from 29 to 40, that's an 11-step jump. Now, in this direction, in the y direction, you should notice also that that's not linear. All right, but what happens is, if we shore up these increments, we're going to start out at this point again, and we're going to start out at this 13, and now we're going to increment by smaller amounts. So now we're going up by 0.5. And you can see here that we go from 13 to 15.25 to 18. That's still not linear. Okay, this is still not linear either. It's not going up by the same amount each time. All right, but what you should notice is that if we make these increments really small, more or less what we're doing is we're taking this surface and we're just zooming in on one little piece of it. And I think you can imagine if you zoom in enough times, you're going to end up with something that looks very much like a plane. Right? And by the time we get down here to a really small increment where we're just going from 2 to 2.01, I think that by the time we get to that point, we go from 13 to 13.04 to 13.08. Now, it's still not exactly linear, but due to rounding, that does look like it is a linear progression. And then we're going to go from 13 to 13.06 to 13.12 to 13.18, and I think that you can see that there's some rounding there. But the idea is that if we zoom in enough on this surface, we end up with something that looks like a linear function or a plane. All right, so the idea is we want to be able to come up with what is the equation of a tangent plane to a surface. Okay, just like in Calc 106, we talked about finding the equation of a line that's tangent to a curve. We want to find an equation of a plane that is tangent to a surface at a particular point. All right, so this is just a repeat of that same table. Now, one of the things that we got to remember is that we did find the equation of a plane before, and we said that the equation of a plane can be found by this function z, or I'm just going to call this f of x and y. Okay, f of x and y is a linear function. And this ordered triple, x0, y0, z0, is a point on the graph. This delta z divided by delta x and this delta z divided by delta y, those are just the slopes in those particular directions. All right, so if I'd like to be able to find an equation of a plane that contains this point and has these two slopes, this is the equation of the plane. Okay, that's what we did in a previous section. All right, so now what I'd like to be able to do is take that one step further and say, how do we find the equation of a plane that's tangent to a surface at a particular point? All right, so let me split the screen here. Okay, and I want to still be able to see that function up there and see how we're going to take that idea and make the equation of a plane that's tangent to a surface. All right, so think about, you got this plane that's tangent to a surface. We want to find its equation. Well, it's going to be in the form of z is equal to z0. All right, let's leave that alone for right now. And let's think about, well, how do we find the slope in the x direction? Well, that's what we've been doing all along here. We've been finding the slope in the x direction. We've been calling it the partial derivative with respect to x at a particular point. Let's call that point, I guess we didn't use a and b, x0 and y0. Let's use the notation we've got up here, a and b. Okay, so we find the partial derivative at that point. We're going to multiply that by x minus the x-coordinate of a point that's on the plane. That x-coordinate that's on the plane is going to be just whatever a is. Okay, then the slope in the y direction, we've been calling that fy. Okay, evaluated at the point of tangency, ab, and then times y minus a y-coordinate that's on the plane. The y-coordinate that is on the plane we'll call b. Okay, then we got to come back here and we got to talk about what is a z-coordinate that's on the plane. Now this isn't necessarily the z-intercept, this is just the z-coordinate of a point that's on the plane. And if you think about when x is equal to a and y is equal to b, what is z equal to? Well, z is just going to be a function of those two things, so that z0 is just the function evaluated at that ordered pair. Okay, so this is basically the formula we're going to be using to find the equation of a plane that's tangent to a surface. Okay, so let's see if we can apply that. I want to keep that formula visible, so let's do this. We'll slide this up. There's our formula we're going to be working with. Here's our example. Okay, so find the tangent plane approximation, also called the local linearization. Okay, and your book does go back and forth between this and local linearization. Here's the function near the point 2, 3. Find the equation of the plane. All right, so what we need to do is z is going to be equal to f evaluated at 2, 3 plus the partial derivative evaluated at 2, 3 times x minus 2 plus the partial at 2, 3 times y minus 3. Alright, so f of 2, 3, that's simple. Just put 2 and 3 in here. 2 squared is 4. 3 squared is 9. 4 and 9 is 13. Plus, we're going to find the partial derivative with respect to x. Partial derivative of this function with respect to x is pretty simple. That's just 2x. And then this says evaluate that function when x is equal to 2 and y is equal to 3. So when x is equal to 2, that's going to give me 4. All right, and then we're going to multiply that by x minus 2. And then we need the partial derivative with respect to y. Partial derivative with respect to y is just 2x, or I'm sorry, 2y. And 2y, when x is equal to 2 and y is equal to 3, that's just going to give me 6. So plus 6, and then y minus 3. Okay, and I think it's fine to leave your answer just like this in this form. All right, if you want to get it into the form that we had talked about before, you know, where you've got z is equal to some number times x plus some number times y plus some number, you can distribute this and combine all your terms on this side and get it in that form. That's fine. I don't think you need to do that much work. Okay, so finding the equation of a tangent plane is pretty simple if you know this formula. Okay, this is a formula I'm going to expect that you have memorized. All right, now the next thing I want to look at is what are we going to do with these tangent planes? Well, one of the things we want to do is approximate the value of a function at a particular point. So if I take this ordered pair 2.02 and 3.01 and plug it into this linear function, I just want to see what's going to happen. All right, so making an approximation here, f of 2.02 and 3.01 can be approximated by plugging those coordinates into this function. So 13 plus 4 times, I'm going to use this x, 2.02, minus 2 plus 6 times the y coordinate 3.01 minus 3. All right, so evaluating that, I'm going to get 13 plus 2.02 minus 2 is going to leave me with 0.02 times 4 is going to give me 0.08. Plus, over here we're going to get 0.01 times 6 is going to give me 0.06. All right, so we're going to end up with 13 plus 0.14, so 13.14. All right, now that's an approximation of what I would get if I took 2.02 and 3.01 and actually plugged them into this function. All right, now I think I've got those values in that table, so if we go back and look at 2.02 and 3.01 in the table, we'll see 2.01 and 3.02, that gave me 13.161, right, which is pretty close to 13.14. We got a pretty good approximation that way. Okay, now the other part of this says, let's do the same thing, but let's approximate the value of the function at 3,4. All right, so if we do that same thing with 3,4, f of 3,4 is approximately equal to 13 plus 4 times 3 minus 2 plus 6 times 4 minus 3. So that's going to give me 13 plus 4 plus 6, that gives me 23. All right, so f of 3,4 is approximately 23, but if you take 3,4 and plug it into this function, you're going to get 3 squared is 9, 4 squared is 16, 9 and 16 is going to give me 25. So the actual value of the function here is 25. Okay, whereas the actual value of the function here, if I remember right, was 13.161. All right, so one thing I want you to notice is these two things are pretty close together. These two numbers are a little bit further apart. Right? And the question is, well, why would that happen? All right, well, if you think about this linear function, this plane, and this surface are going to be pretty close to the same thing as long as you're taking points that are pretty close to the point of tangency. 2.02 and 3.01 are really close to 2,3, whereas 3,4 and 2,3 are relatively further apart. Right? So what you should notice is this linear function is going to give me nice approximations if we pick points that are close to the point of tangency. All right, so this is what we just said. Notice that the approximation gets worse as you move further away from the point of tangency. Okay, the last thing that's in section 14.3 is something called the differential. All right, and what we want to know, well, first of all, let's just talk about some notation. The notation is, we're going to say that this is delta f is the change in the function. All right, this is how much the function changes as we move from an ordered pair AB to another ordered pair XY. This is just how much of a change is there in the function. Okay, and then we're also going to define delta x is just how much x changes from x to a and how much y changes from y to b. All right, so if we just take that equation of the tangent plane, this one up here, and we just substitute in, notice that if I take this f of ab and just subtract it to the other side of the equation, we're going to end up with f of xy minus f of ab. That's just delta f. Okay, so delta f is equal to, all right, so now we got partial derivative of this function with at AB is just f x at AB. And then x minus a, we've agreed that that's just equal to delta x. And then partial with respect to y at AB. And then this y minus b, we're just going to say is change in y. Okay? All right, and a lot of times when we talk about this approximation or this differential, we're talking about, we're going to use this notation. Delta f is just equal to, and we'll just say fx times delta x plus fy times delta y. Okay, just simplifying the notation a little bit. Okay, so the next thing is a diagram that is in your book, and this just illustrates a little bit clearer exactly I think what we're doing, and that is before we did some approximations. And what we did is we approximated the value of that function at 2.01 and 3.02. And so we incremented the x a little bit, we incremented the y a little bit, and then we got an approximation. All right, in that diagram in your book, this surface that you see up here is the function. This is the tangent plane. All right, and then you notice that close to that point of tangency, the two things are almost the same thing. All right, so if we say that maybe this was the point 2,3, and this point is the point 2.01 and 3.02, and we take that point and we go up to the surface. Something's wrong here. We go up to the surface, and we got two different values. We got the actual value of the function on the surface and then the approximation on the plane, and those two things are really close together. And then if we were to go out here to, let's say this is the 0.34, we come up here, we hit the point that's on the plane, here's the actual value of the function. Those two things get further apart as you move away from that point of tangency. All right, so what we want to be able to do is find out what is the change in the value of the function, as we move from one point to another point. Okay, and that's exactly what we did up here. We'll talk about how much does the function change as we move from A to B, from AB to XY. Okay, so what we're really trying to do is approximate what is this change from here down to, this is the value of the function, how much does that thing change? Right, and what we're going to use is how much change there is here. Okay, and as long as the delta x and the delta y are small numbers, this change and this change should be pretty close. Okay, so we think about how do we find out how much of a change there is here. If you look at this triangle and you think, well, this side of the triangle is delta x. Right, so delta x, that's also the length of this side of the triangle. The slope of this is the partial derivative. So if we take the partial derivative, the slope, and multiply by the change in x, we're going to get how much of a change there is here in y. Right? So from this point to this point, that is the partial derivative with respect to x times delta x. That's this piece here. Okay? One thing that's not in the diagram, I think that they probably should have drawn another line that goes across this way. And think about that there's another right triangle here, and if you think about what's the change here, that really is just the partial derivative with respect to y at AB, and then multiplied by the change in y. Okay, if you add those two things together, you're going to end up with the total change here. Okay, and so that's where that formula comes from. Let me see if I can clean some of that stuff up now. Okay, so the change in the value of the function, the delta f, as long as these values are really small, this change from here up to here is almost the same as the change from here to here. All right, now it looks like in this picture that's twice as big of a difference, but we got to think about these delta x's and delta y's are really small numbers, so think about what's happening over around this point. Think about this point being really close to this one. Okay, and then I think you get the idea of what a differential is. All right, so you got some questions that say find the differential at a point. Okay, well, the differential, let me back up just one more step. If we say that these delta x's and delta y's are getting very, very close to 0, then instead of writing delta f, we're going to say df. Right, and df is going to be equal to the partial with respect to x times delta x plus the partial with respect to y, and not delta x, but dx. And then partial with respect to y times dy. All right, this is the differential. Okay, so find the differential down here. To find df, that was find the partial with respect to x and multiply it by dx, and then find the partial with respect to y and multiply by dy. Okay, so find the partial derivative of this function with respect to x. Treat y as a constant. The derivative of this is going to be 2x square root of y times dx. And the partial with respect to y, think of x as being constant, so that's going to be x squared. Partial, or the derivative of square root of y is 1/2 y to the negative 1/2, and then just times dy. Right, so that's all they're asking you to do. For right now, it looks like this is just going to be notation, but this is something that's going to be important later on in the course. Okay, so then I guess it tells us to do one more thing, and that is to find those partial derivatives at this point 3, 4. All right, so find the partial derivatives at 3, 4. That just means plug 3 and 4 in. So this will give me 2 times 3 is 6, times the square root of 4 is 2. That's going to give me, what, 12 dx. And then plugging in 3, 4 here, this is going to give me 9. And then 1/2, 4 to the negative 1/2 is, what, 1/2 again. So 1/4 times 9, that's 9/4 times dy. Okay, another example. Find the differential. This is one where we're just going to give it as df is equal to the partial times dx plus the partial dy. Alright, so all we got to do really is find the partial derivatives of these functions. So partial derivative of this function with respect to x is 2x cosine y times dx plus the partial of this with respect to y is x squared, and then the derivative of cosine is negative sine. So let's do this, negative sine of y times dy. Okay, simple as that. Okay, well, I hope that is a clear enough explanation about 14.2 and 14.3. I think the most important thing that you guys need to focus on is how do you find partial derivatives with respect to x and y algebraically. You know, those first couple problems that I did up here. And then the find the equation of a tangent line is just plugging into a formula that involves some partial derivatives. And then that idea of the differential. For right now, it looks like it's just some manipulation of symbols, but it is something that's going to become more and more important as we get through the course. And really what we're thinking about is how much is the function changing as you move from one point to another point along the xy plane. Okay, so I hope that this is a clear explanation again, and enjoy your weekend, and I will see you on Monday night. In terms of a quiz, I think I'm going to wait until Wednesday of this next week to give you guys a quiz, and there will be a question on there about finding partial derivatives, and there will be some questions about finding equations of the tangent planes. So don't sweat about a quiz on Monday, but there will be one on Wednesday. Okay, and I'll get your tests back to you. I'll have them graded pretty soon, and we'll have them online pretty quickly, probably by the end of today. And today is Thursday. Okay, all right. Enjoy your weekend again, and I'll see you on Monday.